So one of the two big concepts we'll be looking at is BOD. Before we get into our analysis of BOD in the Clampock River, we will discuss what BOD is and what it consists of. So some general concepts about BOD, starting with what is BOD. BOD stands for biochemical oxygen demand and represents the amount of oxygen consumed by bacteria and other microorganisms as they decompose organic matter under aerobic conditions at a specified temperature. Aerobic conditions mean that oxygen is present there. Generally, a high BOD value indicates a higher level of water pollution, while a lower BOD value indicates cleaner, healthier water. Streams, rivers, and lakes include something known as dissolved oxygen, or DO. Dissolved oxygen is a very crucial component of natural water bodies. A sufficient concentration of dissolved oxygen is necessary to maintain life and good quality in the water. Microbes utilize dissolved oxygen in water to break down complex organic compounds present in the water, and marine animals use dissolved oxygen for respiration. We will clarify some common terms we will be using throughout this video as well as the next one. These terms include BOD, exerted BOD, deficit of O2, the reaeration constant, and the deoxygenation constant. I will now go into a little more detail about each of these. So the first one is BOD represented by an L, as well as exerted BOD represented by a Y. When measuring BOD, we will be analyzing what effect a sample has on oxygen available to living organisms in the water into which waste is discharged. BOD is usually the limiting reactant and controls kinetics. BOD is most commonly seen in units of milligrams per liter of O2. We can find the BOD at any time through the integration of a mass balance equation, which will be explained in further detail a little later in this video. BOD exerted is simply the measure of the change of BOD over time, taking the initial BOD minus the BOD at any given time, which can be seen in this graph. Next, we have the deficit of O2, which is represented by the letter D in our studies. The deficit is found by taking the O2 saturated concentration, which is the equilibrium between air and water known by Henry's law, and subtracting that by the O2 concentration at a given time. The deficit of O2 is a way to say how far we are from our ideal scenario. The first graph shows a graph of oxygen concentration over time. We can see on this first graph the difference between the saturated oxygen line at the very top and the curve of the oxygen concentration gives us the deficit of oxygen. This then creates the second graph, which represents only the deficit of O2 over time. Up next, we have the deoxygenation constant and the reaeration constant. These go hand in hand, so we'll go over what these mean individually first and then how they connect. So the deoxygenation constant represents the BOD loss due to a reaction with oxygen and microbes, whereas the reaeration constant represents both the deoxygenation rate plus the rate at which BOD undergoes sedimentation, represented by Ks, but won't be used much for our studies. So with BOD, we have the rate of reaction represented with the deoxygenation rate, as well as this rate that BOD settles to the floor of the stream. And both of those rates combined gives the reaeration rate. We can actually find the total change in oxygen deficit by finding the difference between the deoxygenation rate and the reaeration rate. This is represented on the graph seen on this slide. Now that we know a little more about each of our variables we will be using throughout our study of BOD, we will get into our mass balance equation. So starting off with our BOD equation, we have that BOD is equal to our negative K rate multiplied by BOD multiplied by oxygen. But we don't need the oxygen for this equation, and our BOD is the limiting reagent. So therefore, our new equation would only include our negative K rate as well as our BOD. And for our studies, BOD is represented by L. So then we can rewrite our mass balance equation using dL dt, which is equal to our negative K rate multiplied by BOD, which is L for this equation. So we can then integrate that OD equation and solve for our BOD. So our BOD is equal to our initial BOD multiplied by e to the negative K rate times the time. So we will be using this equation when we are solving for BOD at a given time. Next up, we will be solving for our BOD exerted or consumed. So here, BOD exerted is represented by a y, which is equal to the initial BOD minus BOD, which we just solved for in the above equation, which we can now plug in to solve for our exerted BOD. So this gives us that BOD exerted is equal to initial BOD multiplied by 1 minus e to the negative k times the time. And this equation we will use when solving for BOD exerted. Furthermore, we will be solving for the oxygen concentration at a given time. And so we will need to use the equations we just solved for to find the oxygen concentration. In order to help with solving for this, we want to rewrite what we know about exerted BOD. So we know that exerted BOD is equal to initial BOD minus BOD, which equals O2 initial, the initial oxygen concentration, minus the oxygen concentration at a given time. So we can now solve for oxygen concentration at a given time with the use of these equations. So we can solve these equations by writing what we already solved for with BOD and BOD exerted. So rearranging these equations, we can then solve for our oxygen at a given time, which equals the initial oxygen concentration minus the initial BOD multiplied by 1 minus e to the negative k rate multiplied by the time. And then we'll use these three equations that we have just solved for consistently throughout our studies to find the BOD exerted or consumed, as well as the oxygen concentration at a given time. So to practice what we just learned, we'll preview our quiz. So our quiz consists of a sample equation for finding the oxygen concentration at a given time. In this quiz, we will be given time, oxygenation rate, the initial oxygen concentration, and the initial BOD. We'll then solve for the oxygen concentration at a given time using the equation provided in the video on the mass balance equation slide that we have just gone over.